TK2 YouTube. All right, guys. Well, here we go. Lab number 2. All right. Not a ton of stuff to really go over in this lab. Obviously, this lab was very, very hands-on. We did 3 different experiments, and we were all trying to highlight, hypertonicity, hypotonicity, osmolarity, diffusion, all that stuff in the inside. So there's not a ton of stuff for us to really go over here. I mean, I'm going to fill in, a lot of it is instructions, right? Like this is all instructions here. This was stuff that you guys all determined in class, but the results at least we'll go over, what should have happened. We'll do, some brief descriptions and explanations on things, but otherwise, a lot of this is stuff that you guys should have had for data, and then your summarization of what your findings were, essentially. Okay, so per usual, learning objectives: define diffusion, osmosis, and osmolarity. Explain what is meant by hypertonic, isotonic, and hypotonic solutions. Conveniently enough, pre-lab prep right here has all 6 of those things. So we're going to get that first learning objective out of the way right away. Okay, so let's get rolling here. Okay, so learning objective number 1. Okay, define all these terms. So this is the pre-lab. This is stuff you guys should have done before you came to class, but of course we'll go over it again together. Okay, so what is diffusion? Okay, and you probably had learned about this in high school in some way, shape, or form from a biology class, maybe a chemistry class, but this is the movements of molecules from, oh my gosh, my writing is already off the rails, from high, I'm just going to abbreviate here, high concentration to low concentration. And that could be a general area, right? So that could be, for example, you're letting helium out of a gas, right? So helium diffuses through the air, okay? So helium stuck inside a balloon, you let the helium out, it's going to diffuse from an area of high concentration, right? Because inside the balloon, it's a whole bunch of helium molecules, right? Versus out here, right, in the natural air that we breathe, it's more oxygen that we're breathing in, right, compared to helium. So we're moving the helium from inside that balloon, high concentration, to an area of low concentration out here in the natural environment where we breathe, okay? Osmosis, very similar to diffusion, okay? The only difference is this involves water, okay? So it is the net flow of water across a selective, my gosh, like I said, my writing's all over, permeable membrane, okay? All right, osmolarity. So osmosis and osmolarity are not the same thing, okay? Osmosis is the net flow of water, okay? Osmolarity, what this is talking about, is the total solute concentration, okay, of a solution. So, what is osmolarity? How would you define this? So think about like salt water, for example, okay? Salt water from the ocean. You take a glass out, you take a scoop of it. Inside of that glass of salt water, you have obviously water, but can you see the salt? Most of the time, the answer is no, right? Because the water dissolves it, right? Water dissolves the salt, but it's still in there, right? The salt is still in there. It's just dissolved down into its molecule form, right? So salt is sodium chloride, but as water, dissociates it, it becomes sodium and chloride separated in there, okay? So the sodium is in there, the sodium chloride, that salt is in there, but you can't see it. So that is what a solute is, something that's been dissolved by water that isn't visible, okay? So the osmolarity is the total solute concentration of a solution, okay? That's just an example of what a solute would be. So, and then we have hypotonic, isotonic, and hypertonic, all right? Hypo meaning below, okay? So what does this mean? Having a solute concentration, and that is less than intracellular fluid, ICF, okay? So you have a solution, okay? And then you have something, right? You're dropping something into a solution, okay? And as we saw in this lab, we did it with French fries or potato strips and an egg, right? So you're going to drop an egg into a hypotonic solution. What's going to happen? Well, the hypotonicity basically is saying that there are less solutes in some solution compared to the egg, right? So if there are less solutes in that solution, what's going to happen is that the water from that hypotonic solution is going to move into the egg, right? Because you want to try and have a good balance. You want to have an equilibrium of the solutes. So the water is going to move over from the hypotonic solution into the egg to try and equal out the amount of solutes. Okay, that's what a hypotonic solution is. Iso is a solutes concentration that is equal to that of intracellular fluid. Okay, that's what we want. That's a perfect balance right there. Okay. On the contrary, hypertonic is having a solutes concentration that is more than that of the ICF, intracellular fluid. Okay. So, for example, you put the egg, you take that egg, you're going to put it in a very sugary solution. You're going to put it in, I don't know, a big thing of Kool-Aid. Ton of sugar in the Kool-Aid, right, compared to the egg. So what's going to happen to that egg? That egg is going to lose a lot of its water. It's going to donate it into the Kool-Aid to try and dissolve extra solutes that are in that hypertonic, Kool-Aid solution to try and equal it out. Okay. So that's that. Pre-lab prep, super easy. 6 definitions. That's learning objective number 1. Out the door, just like that. Boom, easy. Okay. All right. Now we have number 2. Describe how various factors affect diffusion rate. Let's scroll down. So what is diffusion? And as we mentioned above, it's the net movement of molecules from an area of high concentration to low concentration. The difference between two concentrations is known as the concentration gradient. Because molecules move from a place of higher concentration to lower, we say that when they diffuse down their concentration gradient, okay? We say that they diffuse down it because it's easy, it doesn't take any effort, right? As an analogy, a gradient can mean a hill. A wagon released at the top of a hill will roll down the hill spontaneously, right? Because gravity will do that for it without the need to push it down. So, similarly, when you eat a meal, a high concentration of sugar accumulates inside the small intestine. The cells lining the intestine contain only a low concentration of sugar. Therefore, the sugars down their concentration gradient. Okay, so the sugars will move from that food onto the intestinal space without the need of energy. Okay, super easy. All right, versus when you're moving up gradient, it takes effort. So diffusion takes no effort. It happens regardless because of high concentration to low concentration. Okay, so it occurs all around us, but the rate at which it occurs is affected by several different factors, which we talked about in lab, and we're going to go over these 6. Okay, so for example, indicate in table 2.2 here how certain factors of diffusion will be affected if something were to increase. Okay, increasing. All right. So if we were to increase the temperature, all right, what would happen to diffusion? So think about it. So if something's cold, it's not going to quite move as fast, right? We think about something that's frozen, right? It's stuck, it's solid. Versus something that's melting at a very high temperature, it's moving, right? So it's going to move a lot faster. So what's going to happen? We're going to see an increase here in diffusion because of the temperature going up, okay? What about the molecular weight, okay? So let's say we're trying to move something that's really, really heavy, okay, down a concentration gradient through diffusion, okay? So the higher the weight, so yeah, you think about this all the time, you're trying to do like a sled push at the gym or something. The higher the weight, the harder it's going to be, right? So because of that, the rate of diffusion is going to cause it to go down, okay? The heavier something is, harder it is to move, the slower it will take, okay? Concentration gradient, okay? So we just talked about that. So if the concentration gradient is higher, aka, room A, for example, we have a very, very small room that is filled with like water or something, and then we have a bigger room, okay, that's filled with more water. These are really bad examples. I'm gonna scratch that. Better example, okay? Think about when you're going for a run or something, okay? When you're running outside and it's 40 degrees versus when you're running outside when it's 80 degrees, which one is easier for you to dissipate that heat? Okay, because remember, your body is building up a lot of heat because it's working out, right? So it needs to dissipate that heat so it can keep your body at a normal temperature. So if it's colder outside, is your body able to lose that heat, or when it's hotter outside? Well, when it's colder outside, your body dissipates that heat a lot easier because that gradient, okay, is a lot bigger. So if the gradient is going to increase, diffusion will increase, okay? Not very fun. I'm a cross-country runner or a competitive, previous Division I runner, and when you're running outside, it's 90 degrees and humid. It's very hard for people to cool down versus when it's 40 degrees outside in the brisk fall air. Much easier to cool down that way. All right, membrane surface area. So the more surface area you have, what's going to happen? The way I think about this, you're trying to get into a stadium, you're trying to get into, Lambeau Field for a Packers game. Imagine how much harder it would be if only one gate was open there, right? You have a ton of things trying to get into the stadium, a ton of people, right? One gate's open. How hard is that going to be? It's going to be really hard, right? Versus if every single gate was open, aka the surface area, all right, was much wider open, it'd be a lot easier for people to get into the stadium, okay? So if we were to have an increase in the surface area, we're having an increase in diffusion, okay? What about the permeability, okay? So we have the gates at Lambeau Field, for example, okay? We have the gates. But let's say that the gates have 3 metal detectors. You have to go through 3 metal detectors. It's not very permeable, okay? It takes a lot of time for you to get through all that. Versus if there was one gate, one metal detector at the gate, that's a much more permeable, membrane or a gate to get into. So you're having 3 metal detectors versus 1 metal detector. So what's going to happen if you increase the permeability? It's going to cause it to increase, okay? Because if you make it a lot easier for people to get in, it's going to be easier for things to diffuse through, okay? Last thing, viscosity. This is referring to the thickness of a structure or a molecule. The way I think about this, you have syrup, you have water inside a canister. When you're trying to dump out the syrup, it takes a lot more effort. You have to squeeze it a lot harder because it's more viscous. So if it's more viscous, it's going to go down, okay? All right, so that's it. So temperature, if it increases, diffusion goes up. Concentration gradient, it's going to go up. Membrane surface area, it's going to go up. Membrane permeability, it's going to go up. Okay, pretty easy. All right, and then we did experiment 1 here. All right, remember we had each of these, different droppers. We had to drop these different solutions onto the plate, put it into either the heater or onto the ice. Okay, and then we had to see, of those solutions, which one diffused further. We were measuring it, obviously. We had to do all that. We waited for a good amount of time. We retrieved the plates. You guys did your measurements. Excellent. Okay. But what happened? Okay. What happened? How did the temperature? How did this? How did molecular? How did all this stuff affect the diffusion distance? What do we see? So what we should have seen, particularly compared to the diffusion distance of each die on plate 1 versus plate 2, as well as plate 3 versus plate 4. So what happened with the temperature? So at the higher temps, there was a further diffusion distance, as we would expect, right? What was the order of that should have happened? Well, if everything went according to plan, what should have happened was 2 was greater than 1, and then 4, and then 3. Should have been what happened, okay? What about the molecular weight? Okay, we have the weights here, 697 grams per mole, 374 grams per mole. Heavier, lighter. So what should have happened here? So diffusion of meth blue should have been further because it weighed less. That's what should have happened, okay? What about the concentration gradient? Okay, so the 0.1 molar, 1 molar. The higher the molarity means that the concentration gradient is greater, okay? So if it's greater, that means it's going to diffuse a lot easier, okay? So the 1 molar diffused further compared to the 0.1 molar blue, okay? And lastly, viscosity. What happened here? So we have comparing the plates, plate 1 versus plate 3, and then plate 2 versus plate 4. We have the number 2 agar is more viscous than the 1% agar. So if the 2% is more viscous, what should have happened here is the higher viscosity diffused a shorter distance. Okay. And what the results should have been for this one was 1 greater, or 3 greater than 1, excuse me. 4 greater than 2. Okay. And then any results that were different from what you expected, you guys should have explained that there. Okay. But there's a lot of error. You know, this is what should have happened, right? There's a lot of things that can go wrong. Obviously, when you put the plates on top of the ice, was it tipped over a little bit? You know, potentially, right? The ice isn't perfect, so there's a lot of gray areas with this experiment. But we're just trying to get you in the mindset of what, you know, how diffusion works and how these, you know, osmolarity gradients work and all this stuff. Okay. All right. So that's that. Next video, osmosis. We're going to cover this and then also talk about hyper, hypo, and isotonicity. Finish up with experiments 2 and 3. Go from there. All right, guys. See you back.